A line of code feels like an idea. A chip is only matter and electricity. So how does a sentence you write become billions of physical actions? To find out, we have to follow the instruction into the machine. Past the screen, through the case, toward the processor at the center, and then deeper still, into the patterned landscape of silicon. Between code and electricity is not one translation, but a bridge of layers. Information crosses that bridge as carefully timed patterns of zeros and ones. At the bottom of the bridge is the transistor, a tiny controllable switch. A small voltage at its gate decides whether current is blocked or allowed through. Real voltage is messy and continuous, but computers need decisions they can trust. Thresholds turn uncertain signals into clean low and high states, 0 and 1. One transistor can switch. Groups of transistors can answer simple logical questions. A NOT gate flips a bit, while a NAND gate rejects only the all-one case. NAND is a universal building block. Copy it, connect it, and richer logic appears. The same simple gate can be arranged into AND, OR, XOR, and much more. XOR gives the sum bit, and produces the carry when both inputs are 1. Add one more carry input, and the tiny circuit becomes a full adder. Chain full adders together, and each stage passes its carry to the next bit. 4 small decisions cooperate to turn 0101 plus 0011 into 1000. Cross-coupled gates can feed their result back and keep one bit alive after the input disappears. Set writes 1, reset writes 0, and hold preserves the state, the beginning of memory. Registers keep the processor's working numbers close enough to use immediately. Those values enter the ALU, which performs arithmetic or logic, and writes the result back. The clock is the conductor, a repeating electrical rhythm shared by the whole processor. On each rising edge, the program counter, registers, ALU, memory, and input-output advance together. A machine instruction is not one undivided number. Its bits are divided into fields with different jobs. The decoder turns those fields into an operation, a destination, a source, and sometimes an immediate value. First, the CPU fetches an instruction from memory using the address in the program counter. Then it decodes the instruction, executes it, writes the result, and begins the cycle again. A tiny program can load a value, add to it, store the answer, and jump back to repeat. Every visible result emerges from this rapid loop of instructions, data movement, and transistor switching. Writing raw binary directly is exhausting. Long bit patterns are difficult to read and remember. One misplaced bit can change the instruction completely, so programmers need meaningful symbols. Assembly language gives those bit patterns short names such as MOV, ADD, and jump. An assembler maps each mnemonic back to the exact machine code pattern the processor expects. High-level languages let us describe an idea, such as total equals a plus b, instead of managing opcodes. That single line may expand into many loads, moves, arithmetic operations, and stores underneath. A compiler crosses the abstraction bridge by translating human intent into lower-level instructions. The assembler finishes the journey to machine code, the binary words that enter memory and the CPU. Now follow one line end to end. It is translated, fetched, decoded, and executed. Billions of transistors switch, signals travel outward, and pixels light up with the result you can see.